Hello, sir. You can proceed, sir. Thank you.
Okay. Okay. Thank you, sir. Okay. So, good evening, everyone. I hope my voice is clear to everybody. So,
Good evening, sir. Yes, clear, sir.
good evening. Good evening. So, a brief introduction for me. I'm a Vikas. Uh, Currently, I just joined MSc Statistics from IIT Kanpur. So, and for the background, I have an MS in mathematics as well. So, we are going to discuss about the probability theory. So it is a course we will discuss in the manner that whatever you doubt have, you can ask at any time. And more than that, it's a kind of discussion. Why I'm saying it is a discussion? Because I feel the way of learning, like the method of learning is good when we are in a kind of discussion. So, have you ever heard about probability theory, right? So let me, I have seen your papers, like the kind of questions you will see in your exam during when you will face the exam. So I see that there are two aspects. That is, one is probability theory, and the second one is statistics. So one thing you have to clear in your mind that both the subjects are different. This probability theory is something like it's a very short note, or it's very short descriptions of something that uncertainty. What is the chances of happening some event? So this theory is somehow is very small, and statistics is something that we in which we use to handle the data. When we are going to handle the data, on the basis of the data, we are going to predict what's going to happen in the future on the basis of this data. So for that happening of chances, like what is the chances of happening, for that we use probability theory. So somehow these statistics and probability collectively make a good subject that we call statistics and probability theory. Okay, probability theory you have learned in your earlier classes like plus 1, 2, we have seen that what is the probability. Now in this course, we are going to study axiomatic definitions of the probability. It means that what I mean by axiomatic definition of probability, that the probability you have learned earlier, that only contains the basic definition that is called favorable cases upon the total number of outcomes, that is the probability of happening of any event. But here we will use some axiomatic definition. I hope you are aware by axiomatic, what I mean by axiomatic. Like in group theory, when we study the group, we have some 4 or 5 axioms. When we study topology, we have 4 or 5 axioms that should be satisfied. Then we say that the space is the whatever group or the topological space. On the same manner, we are going to define the probability. Then the space. Okay, let me start by very crucial example. So if I toss a coin, I know that head and tail will appear. H is denoted by head is denoted by H, and this tail is denoted by T. So before defining this, I let me tell you something that experiments. Whatever we are going to study, we are going to study through the experiments. Before before starting a study, let me tell you what is experiment. Experiment, it has a mathematical definition, but you can say experiment is some activity we can perform again and again to collect some data. For example, if you toss a coin, head or tail will come. If you again toss a coin, head or tail will come. It means it is a kind of experiment. Let me write the proper definition of the experiment. Experiment is said to be experiment if all the possible outcomes of the experiment are well known in advance. There are 3 conditions. That is, all the outcomes are well known in advance. It means if I do some experiment, I know what is the possibility of happening. I mean, if I flip a coin, head or tail will come. That is the only possibilities we have. If I throw a dice, 1, 2, 3, 4, 5, 6, only among 6 numbers, one will appear. That I know that all the possible outcomes of the experiment. The second axiom of experiment is outcome of a particular event, or I can say trial or performance, cannot be specified in advance. It means I know that these are the possibilities. One of the possibility will happen, but I cannot predict which possibility will happen. For example, I flip a coin, I cannot sure that head will appear or tail will appear. Anything can happen. That is, outcome of a particular trial cannot be specified in advance. The third axiom of experiment is that the experiment can be repeated under identical conditions. Okay, so this is the definition of the experiment. So we are going to study whatever the data we have on the basis of the experiment. And what is experiment? I hope this is clear to everybody. Okay, so now before using anything in mathematics, first we have to define what is the meaning of that particular word. Okay, now I know whenever experiment is happening, I know what is the possible outcomes. For example, if I throw a dice, 1 to 6 are the numbers that can be possible. In any experiment, whatever the possible outcomes is, I will call that collection as a sample space. So, definition of sample space is all the possible outcomes, or I can say collection of all the possible outcomes. Collection of all the possible outcomes. This is I will refer as sample space, and usually I will define sample space as omega. I mean, if I throw a dice, what is the sample space? That 1, 2, 3, 4, 5, 6. And if I throw a coin or I toss a coin, what is the sample space? Head, tail. If I, let me call it omega 1, omega 2. And if I throw one coin, I mean to say throwing means like rolling a die. So one coin, that means flipping a one coin. Okay. When I throw two coins, then what is the possibility that head can come, head tail,
HHT,
and tail.
THTT.
Huh. Okay. So throw two coins at a time and throwing one coin two times is same. Okay. I hope you understand this. So these all are random experiments. These all are experiments because these three satisfies all the axioms of the experiment. And one notation I hope you know in that is A cross B. For example, if this is my set A, this is my set A, and this is same B. A and B are the same set, then A cross B is defined by the collection of X, Y such that X belongs to A and Y belongs to B. These are the pairs, right? So this will be head, tail, head, head, tail, 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 head. This is the same, and you know that I am just rearranging the order. In a set, you can rearranging the order of the element and it will not make any effect. Similarly, if I throw a dice 3 times or I throw 3 dice at a time, then what will be the sample space? I can say that I, J, K will be happen, and I, J, K will belongs to the set 1, 2, 3, 4, 5, 6. I hope this is clear to everybody. If anything you have doubt, even in the minute or anything I write, please just let me know, because we are going to study step by step, and every step, everything I am writing here is important. Now we are not in, for example, let me write something easy example. If I throw a dice 2 times or I throw 2 dice at a time, what will be the sample space? This will be ij, such that I and j will belong to the set 1, 2, 3, 4, 5, 6. So this will be the sample space. Let me call it 4, and this is 5. Omega 5 is the sample space when I throw 2 dice. Now, if I plot them, what will be the open like representation of the set 1, 1, 1, 2, dot, 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 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 6, 1, 6, 6. So this is the representations of the omega 5. I mean, when I throw 2 dice. Here, somebody can ask, what is the probability of this particular? I would say this is the event. What is the event? We will define mathematically as well. But in an experiment, you can say what are the total possibilities. I mean to say, if I throw a dice, if I flip a coin, or whatever I am doing an experiment, there are some possibilities. What's gonna happen? I have a sample space. Every element of the sample space is an event. At this moment, you can take it as the event. So somebody can ask that what is the probability of 1, 1. Then you can see that when I throw a dice, every event, the possibility of happening every event is same. It means these totals are 36. Then what is the probability of this happening particular event is 1 by 36. 1 is the total favorable cases of happening 1, 1, and 36 is the total outcome. That is the basic definition. I would say this definition we have studied in our earlier classes that I'm going to use. For example, if somebody says that what is the probability of happening, if I will denote P bracket something to denote the probability of some event. If I say what is the probability of happening 1, 1, 1, 2. So you can see that the total possible outcomes of happening these two events is 2, and the totals are 36. So probability would be 2 by 36. No doubt, whatever the axioms we will define for the probability will satisfy these conditions as well. Because what we're gonna do, we have to define the random variables in our next classes. For that, the definition of probability is somehow necessary part to define the axioms of the definition. Surely, that definition will be the generalization of this basic definition. Okay, so we have generally we are interested. We are not interested in defining that what is the probability of coming 1, 1 or 1, 2 something. We are generally interested in those kinds of event where some conditions is given. I mean to say, if I throw a dice, what is the probability that dice will show that the sum of the dice on the two numbers is say 7 or say 8, then the event or whatever the favorable cases will be changed accordingly. Then before that, I should define what is the event so that you cannot go out of the event space. So event, I will say what is the event at this moment. If you have omega, omega is a sample space. At this moment, you can consider omega is a finite set or countably infinite. I hope you are, if you have any doubt in countably infinite or uncountable, or we can discuss a little bit. But sorry. Okay, if you have a omega that is a sample space I mean to say, total possible outcomes, it can be finite or you can take it as countably infinite. No doubt we will go to uncountable set as well when the omega is an uncountable set. Then you just take power set of omega. Power set of omega is the collection of all the subsets of omega. For example, if I have omega as head tell, then phi ht as t. This is the power set. This is the power set of this omega. So I will define event as event, the subset of power set of omega is called event. For example, anybody can listen. This phi is by definition we are taking here as event. Head tell. Somebody can ask, if you flip a coin, what is the possibility that head or tail will come? Head or tail will come. Definitely head or tail. This event has probability 1. This event has probability 1 by 2. This event has probability 1 by 2. I don't feel that it should be, at this moment I would tell you, because you know already this. This is, we are taking it, it is in mathematically, it is known as biased, sorry, unbiased. Unbiased coin. Unbiased means fairness. This is a coin where coin cannot stand on its edge. Either it will show head or it will show tail. Okay, you can see that if omega is a sample space, then power set of omega will contain phi and omega. So omega and phi are considered always as an event. By definition, we are taking it. And this power set of omega we call as event space. This is the event space. We will call it as event space. Whatever the probability you will ask, that should belong to your event space. Okay, instead of this finite, countably infinite, if you take omega as to be 0, 1, omega has to be 0, 1. Can you tell me any experiment whose outcomes come from closed interval 0 to 1? Any experiment? For example, if I have a line, real line, I put a thread. This is the thread. I bound it here. I bound it here. And this is 0. I call it 0. And this is 1. If I throw a ball on this thread, what is the probability that thread will hit one of the point of this line? Then that point or whatever the ball I am throwing, that can hit any point of this line. Then this will be the omega. This will be the sample space. In that case, the sample space is uncountable. Now the power set of omega. Have you heard about what is the power? This is uncountable. So I believe that you know that what is the power set of this closed interval 0, 1. If you don't know, you just think that whatever the subset we are going to take, that will be the event. That will be the event. There is no need to go in very deep of this. You know what is uncountable or what is the power set. Power set, you know the definition. If there is any set, then every collection of every subset of that set is known as power set of omega. And you can observe one thing more. So now I am just telling you the basic definition that we are going to use in our analysis. I mean, in whenever we will use the some advanced technique how to handle that, what is random variable or those kinds of things. So you can see that whenever E belongs to power set of omega, then E complement also belongs to power set of omega. that is easily observable. That's just a part of set theory. So similarly, you can observe one thing more. What is that? For example, EI belonging from, you can say that is natural number. This is the collections of the sets, and EI is subset of power set of omega. It means you are taking collections of the events that is countable because I is belonging from natural number. Then union of EI, that will belong to power set of omega, and you can say intersection of EI, that will also belong to power set of omega. You know that if a how to say that omega is a set, then p omega is a power set, then intersection, union, complements all belongs to the power set of any set. That is just a set story. I'm just recalling you. Okay, so we will not use uncountable union of the intervals. We are just using here countable union. We will not use the notion of uncountable intersection or an uncountable union. Okay, that is a separate issue we will handle sometime later. Okay, that's known as whatever we have done in our earlier classes. It is known as priori definition. That is priori probability. Priori probability, or we call it as advanced, right? Advanced. Sorry, classical. That is known as classical definition. What is mean by classical definition? The definition we have used in our earlier classes. Earlier classes, I mean to say, you have learned in plus 1, 2, or graduation. That is what is the classical definition we used to say. What is the probability of happening an event is equals to number of favorable cases upon total outcomes. That is the priori definition. For example, if E is an event and the total favorable cases, what is the mean by favorable cases? For example, if I have omega as a sample space, then in omega, if I say what is the probability of event E, the subsets, or you can say the subsets of power set of omega where E present. Then if I say that okay, let me write. If E is a subset of power set of omega, right? This E I am taking. E I am taking. Then what is the probability of power set of omega? Sorry, probability of E. Then say ki union of EI. EI. What is EI? EI means E is subset of EI upon में power set of omega and the cardinality of this. I hope you understand the cardinality. Cardinality means it's the potential of the set. It means we are dealing with sets. Omega is a set, power set of omega is a set, and a set has cardinality means I think the number of elements present in that set. That is the cardinality. So this is the priori definition of priori probability, or classical definition, you can say. Okay, total number of favorable cases. Right. Okay. Probability of E of favorable cases to E. Okay. Okay, so this is known as the priori probability definition. Okay, so now we will study the definition, that is axiomatic definition. The axiomatic definition, whatever we have to study in mathematics, it should be axiomatic. It means there are some, standard postulates. Any set satisfies those postulates, then we will able to study the properties, like which is covered in those whole subject. I mean to say, if let me define what is a set function. Okay, anybody want to tell what is set function? What is set function? What is function? Can anybody tell? What is function? Okay, function is something that rule we assign. Like if I have set, I feel that you know what is a set. Set, what is set? Set is something
Collection of the element objects
collection
and
of the
well-defined
Collection
collection.
of well-defined objects.
Well-defined collection of the
well-defined
objects. And objects are
Okay.
not
Well,
required.
a well-defined collection of distinct objects. Okay, okay. I would suggest you to remember the definition as the standard things. You don't change, don't put any your words, because your definition are somehow names. Like if my name is Vikas, somebody cannot say that I forget the V. Okay, so definition is the name of something. So whenever something happened, a set, what is a set? A well-defined collection or distinct object. You have to add no words. You have to remove no words. Okay, set. What is a set? So if I have a set A, if I have a set B, if I define some rule, I can say. If I define a rule something, what is the mean by rule? That this set have elements and this B set have element. Why they have element? Because it is the definition of the set. Every element of A is related to some element. Some elements say Y. And in the definition of the function, what we use, if A and B are the two sets, then the function from A to B is a rule assign A to B such that every element of A has a unique element. Every element of A has a unique image as the element of B. What I mean by unique? I mean to say this is the X. This belongs to A. This cannot have two images. This only have one image. This is Y. No doubt, there are elements like say Y1 is the image. There are elements in the B. What is B? B is known as codomain. There are elements in the codomain more than one who has three images as X. It means X1 that X1 going to Y1 and this is the X2. This element can two elements can go to one, but one element will go to one only. This is the definition of the function. So if I define what is the what is the real function? Anybody can say what is the real function? If the codomain is the real, if I define a function from A to R, if the codomain is real, this is known as a real function, right?
Real function.
This is known as real function, and analogous to this, I can define set function, but a little bit change because I am defining it, right? What is the meaning by the definition is somehow name. You can give name to anybody, right? You can question on definition ever. So what is set function? I will define set function as a function from the collection of the set to the real. Okay. For example, power set of omega. Power set of omega is what? Collection of the subsets of omega. So I can define a function from this, or I can define a function from omega to say R. This is a set function. This is a set function, right? Let me name it 1, 2, 3. And I can define a function from omega to F as well, or say power set of omega. Power set of omega. This is also a function because in the definition of set function, what I am taking, the domain should be collection of sets. Okay, so now we are ready to define our basic most important thing, that is, for example, if I define a function, okay, I have defined omega as sample space. I have already tell you. This is sample space. Let me define. This is F. F is as a power set. Okay, power set F. If I define a function, let's say omega to no omega to Okay, f2 close interval 0 1. Okay, so I name it as say function p. I define a function p from f2 close interval 0 1. What I mean, like for example, let me take the example as well. For example, omega is say head of l, and our set of omega means here value of f would be I had l at l, right? So this is the power set of omega. If I define a function from pf2 close interval 0 1 such that p of omega is 1. The second thing is p probability or p of e is greater than equal to 0 for all e belongs to f. Okay, and the third one is okay. So I hope you will not scared about this. En, where n belongs to natural number, is a sequence. Is a sequence of events, right? Sequence of events. Why I am calling these events? Because these are, or say e, i's are the subsets of the f. Okay, is a sequence of events such that what is the condition on the event such that e I intersection ej equals to phi whenever. Okay, I will explain it. Don't worry. I not equal to j, then 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 probability of union of uh, I1 to infinity uh, okay, in I that equals to sum of the PEI I is 1 to infinity. Okay. So this is the definition. So then if these three conditions, I will explain these conditions to you guys. Don't worry. Okay. So let me first complete it. Then P. Okay. So this is notation. Okay. Notation is omega f and p is called probability space. This is okay. So I'm sorry for my writing. Okay, so these are the initially it's a long time I'm writing the fan tablet. I will take them in 1 or 2 days. Okay, so p is a function from f to close interval 0 1. What is p? P is the power set of your omega. Whatever the experiment you have a whatever the experiment you have in your, whatever the experiment you are performing, you have a sample space, you have a set as a sample space, you have power set of that set, you are defining a function form that is named as p to the closed interval 0 1. Of course, omega, what is omega? Omega is the whole collection, that is element of omega. The p of that one should be mapped to 1. Okay, you can say it as a probability as well, or the probability of that omega should be 1. And whatever the e you choose from this f, the probability should be greater than 0. And the third one is important one. Whenever you have a sequence, it means you have a collection of all the subsets of the omega. It means whatever the sequence you choose from this f, e1, e2, e3 are the subsets of these f. What is the condition on f? That all these should be disjoint. What is mean by disjoint? That they don't have any common element. Okay, so these are disjoint. Whenever they are disjoint, then these are the sets. Of course, I can write them as a union. Then the union have a set. Then probability of that set will be equal to, if you individually write the probability, sum will be equal, and you have to take care that I is from 1 to infinity. I is from 1 to infinity. So let me check this definition on. Okay, let me check this definition on this omega and ft. I hope. Okay, we will come back to this as well. So if I have omega as at 10 and power set of omega, that is f. Okay, at 10. Okay, so I define a function from P F2 close interval 0, 1. And what is the first axiom? The first axiom is, if I define what I define the probability of this H. If I define 1 by 2, is the probability of T, I define 1 by 2. Okay, this I am defining. After defining probability, I have to check that those three conditions if are satisfied, then I will say this is the probability space. Otherwise, it is not. So now you can see what is the probability of this head tail. That will be equal to probability of head. Okay,
Plus
so
probability of tail.
okay, so why I can write this? Okay, so left hand side equal to right hand side. Why I can write this? Why I can write this? Okay, so I will come to this point as well. Okay, so this is a question mark. Why I can write this? Okay, you have to question every step of mathematics. Okay, so this is one. Okay, so this is one. And the second definition is whatever the E you take, it means you have to take E from this set. Okay, okay, let me check what is this. Okay, whatever the set you take from this set, this is this probability of phi. This probability of phi. Okay, so probability of phi I don't know. Probability of phi
By
I
four.
don't. Okay, why I can write this? This is 0. This is 0, you know. Probability of head we have defined as 1 by 2. Probability of head tail we have defined by 1 by 2. Sorry, this is 1. And no, this is a question actually. This is a question. Why it is 1? Because we have defined only the probability head and tail as 1 by 2, 1 by 2. I don't know that this left hand side equal to right hand side. So, since I am writing it 1, I will explain the reason as well. So, probability of head is 1 by 2. That is by definition, probability of tail is 1 by 2. Okay, so this is just a, okay. So now, whatever the EIs you choose, whatever the EIs you choose, okay. So before defining this probability, we have to define some, definition. Okay, let me go to the back. So this is the function. Okay, so this is a function. Assume that this is the function we are going to define on any sample space, and this is the probability of omega, and these three conditions are satisfied by that function. Before defining this definition on this particular experiment, let me define some properties which are important to defining the probability on the experiment of flipping a coin. So, you know that, okay. What is the third axiom? Third axiom says if, always remember that. I hope you are writing whatever, and at this moment you have to write, because I'm going to connect the, I'm not going to show that previous slide every time. Take the reference of that slide. Okay, I will share the notes as well. I have a proper notes of these everything. So step by step, whatever you miss, you will catch that. Third axiom is, okay, I just write simple thing that I have a function of P at F2 close interval 0, 1. The third axiom says that n belongs to natural number such that EI intersection EJ is phi. Then probability of union is I is 1 2. Sorry, this is infinity. This is infinity. Okay. So I am again saying that this is the definition of a third axiom, and definition you have to remember as the R. Now if I take let us take E1 as omega, E2 as say phi, E3 as phi, and so on. En or phi as n tends to infinity. Okay. So I am saying that the first set I have taken omega, and every those set is phi. Now you can see that whatever the two sets you choose from here, their intersection is phi. Their intersection is phi means EI intersection EJ is phi whenever I not equal to 0. Okay. So this condition is satisfied. This implies what I can write, that probability of union I is 1 to infinity EI, that I can write as probability of EI, and I is from 1 to infinity. This is the third axiom. Okay. So now you can see that this is omega. E1 is omega, E2 is phi. Whenever you take union, their union would be, okay. Somebody tell me what what will be their union?
Omega itself.
Omega itself. Very good. Okay, so I can write the probability of omega. Now I can write it as omega 2 to infinity probability of E2. Okay, you can see that E2, E3, E4, everything is phi. Okay, so so this probability of omega by first axiom, what is it is 1, right?
Yes.
And what is probability of E1? E1 is what? E1 is omega itself, and this is okay. So this is probability of E1, probability of E2. So I can write it as what I can write it as. Let me see the proper notation. How should I write it? Okay, so this is limit m tending to infinity m minus 1. Okay, so probability of 5. Why this is so? Because you can see when I these all are equal. Let me see that this probability of E2 and sorry EI and I is from 2 to infinity. What is this? Probability of E2, probability of E3, and so on. It is going on. It is going on. It is going on. And what is E2, E3? This is probability of phi plus probability of phi, and so on. This is probability of phi. So how many times it is coming? How many times it is coming? If total
M
are
minus
M minus 1 time.
m minus 1. If total is m, and take care that limit m is tending to infinity, and this is probability of phi. So this is the same thing I have write it. And what is the probability of omega? 1, right? So let me write.
Yes, sir.
Okay. So 1 equals to probability of omega plus infinity m minus 1 probability of phi. So this is 1. This is 1. Okay. So this is the thing. Okay, so this is cancelled. And this you don't have any logic, right? You know that the real numbers have these kinds of property. So limit m tending to infinity m minus 1. So here you can see that this is infinity. This is, I don't know, but the product or the limit is going to be 0. It means there is a rule when you have a limit in which one is going to infinity and the whole limit is equal to 0, then second must be 0. Then second is must be 0. So this is a kind of homework if you want to know the reason. So this I can say that probability of phi is what? 0. Okay. So from those third axioms, I have drive the equation for that. What is the probability of phi? The probability of phi is 0. So it is not by definition. You cannot say directly that probability of phi is 0. You have to have a logic. Okay. Now let's come to something. Now let us say E1, E2, E1, E2 are the I can say E2, E1, En I am taking. These are the subset of F. Okay, so these are the subsets of F, and let me take En plus 1, En plus 2 as everything is phi. For example, n value of n is phi. Then E1, E2, E3, E4, E5 are some sets of belongs to F, and everything else E6, E7, E8, everything is equal to phi. In the previous example, we have taken E1 as the sample space, E2, E3, E4 as the phi. Now I am taking some finite subsets of the F, then everything else is phi. Okay. So now what is the condition of these E1, E2, En such that E1, E1 intersection E2, E1 intersection E3, everything is phi. Similarly, these whole are pairwise disjoint. Remember, I am saying these whole E1, E2, En are pairwise disjoint. It means whatever the two sets you take, if you take their intersection, that will be empty. And these whole are En plus 1, En plus 2, everything is phi. So this condition is satisfied that Ei intersection Ej is phi for all I not equals to 2. Okay, so this condition is satisfied. Though from the third axiom, what I can write? Okay. Okay. What I can write as union of 1, 2. Okay. infinity. Remember, this is the third axiom I am using, but third axiom says that if E1, E2, En, this is a sequence which is disjoint, then I can write the probability of EI is sum of probability of EI, that is I equal to 1 to infinity. That is the thing. Okay. So let's move to the next slide. We see that this is probability of E1 union E2 union E3 union union En plus 1 union this, that is going to be probability of E1 probability of E2 plus probability of En. I am just expanding that summation En plus 1 and so on. What is En plus 1? This is pi. This is pi. So this is 0 because we have proved it, right? Earlier we have proved this is 0. So,
Yes, sir.
so this, remember the condition on these En, right? These are disjoint. Okay, so this is, and what is the union of this? This En plus 1, these all are empty. So union will be E1 union E2 union En. This is the thing. So if now I'm just writing note. I'm just writing if E1 E2 En are okay. I'm so sorry for this. No, push. E1 E2 En are pairwise disjunct. Pairwise disjoint, right? Disjoint, then I can write this. Now, let's, for example, for specification, let me take En equal to 2. If E1 intersection E2, E1 intersection E2 is 5, then what I can write from this? That probability of E1, probability of E1 union E2 equals to probability of E1
Plus probability of E2.
Okay. Okay, so this is the. So now we are ready to define that whatever the probability we need for this. Okay, so let's come to this. Probability of head I defined 1. Probability of tail I defined as 1. Now what is head tail? Head, let's take it E1 and let's take it E2. Let's take it E2. Then probability of probability of E1 union E2 because they are disjoint. Okay, in one experiment head is only happening, and in other experiment tail is only going to happen. And E1 E2 are disjoint. That then I can write P1 E1 plus P E2. The same thing I have, right? So this is the probability of head tail because this is the union of E1 E2. So I can write it as, okay. So I hope this point is clear to everybody. That's why I can write. So this is what? This is probability of omega. So okay. So this is probability of omega, that is coming to be 1. Probability of phi equals to 0. Probability of head is 1 by 2. Probability of head tail is 1, by, we have defined it. No, it's a drive. And probability of head is 1 by 2. Probability of tail is 1 by 2. Now you can see that whatever the sequence you take that are disjoint, you will observe that you will able to write it as if E1, E2, En and into infinity is a sequence of disjoint, what are the events. Then I can write it as infinity EI. Okay, so 1 to infinity. So you can see that this first axiom, that probability of omega is 1. The second axiom, that whatever the event you take, the probability is going to be non-negative. What I mean by non-negative, it cannot be negative. It is either 0 or positive. So it is satisfying. And the third axiom, you can check that it's you don't have to check, you just have to write this line that these third axioms is satisfying. So this is a probability space, this is a probability space. So from here I can say that from the axiomatic definitions we cover the classical definition of that probability as well. Now let me get that what is useful to us. Okay, let me go what is useful to us. Okay, what is useful? Okay, so let's take the same example. This is head, this is tail. Okay, so power set of omega I don't need to write, it is as L F. Okay, you know it, what is coming. If I define probability of head as 1 by 2 and sorry, 1 by 2, no, no, 1 by 2. Probability has p, small p, and probability of tell is that is 1 by 1 minus p. Okay. So now if I check what is the probability of omega, what is the probability of omega? That is head tell. So you know that these are disjoint, then I can write it as probability of head plus probability of tell. Okay. Probability of head plus probability of tell. So that is p plus 1 minus p. That is 1. That is totally 1. The second is that whatever the event you take, either you take head or you can say that what is p, for just to make the second condition true, if I define p as this 1. So this is 1. Okay. P is between 0 to 1. Then probability, either it is p or it is 1 minus p. It is in the all cases positive. So you can see for all e belongs to f, probability of e is greater than 0. And for the third, you can write the same line because whenever you see that if E1, E2, E and the sequence of the events is disjoint, then you can directly write the sum of the union is as the sum of the individuals. So third axiom is satisfied. So you can see that here, if you define probability of head as 0.2 and probability of tail is 0.8. This is also a probability space. So it is not compulsory to define that every event has same outcome possibility. It's not like that. It's not mathematically true. Okay. So now the third one more note we can see that we are going to use very frequently. If suppose what I have derived, like if E1 and E2 are the two events such that their intersection is pi, then I can define as probability of E1 union E2 is probability of E1 plus probability of E2. This I can write. This is as simple as possible, right? Now I define E as an event and E complement. You can see that if I take this is belongs to F. If I take A E intersection E complement, that is pi, that is satisfying this condition. So then I can write probability of E union E complement, that is probability of E complement. What is E union E complement?
Omega.
Omega. That is omega. That is E complement. So this is 1. So this is probability of E. So then you have seen this result, I think, so many times, that probability of E plus probability of E omega or E complement is equal to 1, or you can use it as probability of E as. So this is the result we have used many times. Okay, and we are going to use it very frequently. Okay, so I feel this is the definition we have covered. Okay, so today we will do until this. Okay, so just give me some feedback. Did you get everything what I have taught you guys, or something that 40%, 50% you have catch? Okay, it's time to talk for you. I think you can talk, and you can also open your video camera if you don't shy that much. Okay, then. So they are quite okay. So do you have any doubts in this whatever I
No,
have
sir.
teach you today? Okay. So
Sir,
tomorrow we will go.
we can tell like this, no, sir. The probability will always lies between 0 to 1, right?
Yeah, probability is always right. Yeah, you can say, because what we are defining, probability is a function from, this is f to this. That's why this, whatever you take, this will always give a number between 0 to 1. So this is 0 to 1 always. By this definition, or whatever the definition, in classical definition what we used to take, that the probability of probability of any event is favorable outcomes upon total outcomes. You can see that this is the favorable. Okay, this is the favorable outcomes upon the total outcome. You can see that this denominator is always greater than this numerator. Okay, so this always going to be equal to 1. Okay, so favorable outcomes can be 0. It cannot be negative, right? So it will always this. So from there, it is probability is 0 in 0 to 1. And here we can see that this is a function that whose range is between 0 to 1. So from this or that on the both case, probability of any event is greater than 0 and less than 1. Okay, anything else?
No, sir.
Okay, so can we stop today? Okay, so if you have any query, please tell me. Otherwise, we can leave. Okay, any queries?
No, sir.
No, sir.
Okay, then goodbye. Huh? See you tomorrow.
Thank you, sir.
Okay. Thank you, sir. Thank you.
Thank you, sir.